Well, welcome everybody. My name is Curtis DeSaley. I'm the Director of Technology here at Geometric Solutions. And shortly you'll be listening to my friend and cohort, Dan Turk, about additive manufacturing, reverse engineering, and topology. Oh my. Dan, take it away.
Thanks, Curtis. I really appreciate the oh my that you gave. And hopefully through this presentation, that's what everyone online is going to get to say for themselves. So for the agenda, we're talking about additive manufacturing, or it's referred to a lot of times as AM. So how to get the most out of our new product. And additive manufacturing, or 3D printing, as many refer to it, it's more than just prototypes. It's also more than just toys. So how can we industrialize this? And then we're going to look at my favorite software, NX, and see how it is the end-to-end solution. Again, my name is Dan, and I work with Geometric Solutions, part of the Waltonen family. So the Waltonen family consists of an engineering company in Warren, Michigan, with hundreds of engineers, the Geometric Solutions, my company, where we sell software solutions, and then Independence Tooling Solutions. So when it comes to design and manufacturing, you could say that the Waltonen family, it is an end-to-end solution. The owner of our company, he put it best. He said, our ability to successfully partner with our customers comes from our experience in using the tools we sell every day. So NX is my favorite tool. Why? Because I use it every day. So let's get started talking about additive manufacturing, reverse engineering, and topology optimization. Oh my, is what you might be thinking. We can think about these as 3D printing. Now with COVID-19, 3D printing really came to the fore because there was not enough personal protective equipment. And so anybody with a 3D printer, well, they were printing the different pieces for face shields. 3D printing has also been used quite a lot for gadgets, something to hold up your phone. A lot of times people are making toys with it. And then we use 3D printing a lot for prototypes as well. Now, let me just ask my cohort, Curtis, how have you used 3D printing yourself? Any cool things you've done?
Well, I'm a mentor on a high school robotics team, and we use 3D printing all the time. Sometimes we need a bracket to hold a motor. Sometimes we need a protective cover so the other robots don't damage pieces. But we're 3D printing all the time. In fact, our team owns three 3D printers. So we're using it for all different kinds of things. I mean, it's a simple plastic extrusion type printer, but the kids are creative. They design it in CAD and make these useful tools that would be hard for, I'm going to say, a club to make because we don't have every tool that a machine shop would have.
Okay, very nice. And we'll give a shout out to that team, Go Thunder Chickens.
Hey, thank you much.
No problem. When it comes to industrializing additive manufacturing, so that's kind of taking what Curtis just mentioned that the high school team is doing, making just a few pieces, one-offs, but then actually industrializing it or using it for production. That's where the oh my comes in. We can think of this as the 3 R's of AM, or additive manufacturing. Reimagine products, reinvent manufacturing, and rethink the business. We're going to look at these in more depth. So the first, it comes to reimagine products. With NX, we're offering new tools to design the next generation of products for additive manufacturing. You can take advantage of what's called generative design, where the computer, it actually assists by iterating on calculations to create these complex, optimized, kind of organic, funky shapes. And it's not just that it's cool looking, but whatever the performance goals, the strength, if it's light enough, it's able to take care of all of that. We also have what's called Convergent Modeling. Now, this is an amazing tool because oftentimes if we're going to get any scanned data in, it's almost useless. You just can't work with it. But not so with convergent modeling technology. You're actually able to take that faceted geometry or those faceted surfaces, that's just one big blob, and you can go ahead and start working on it. If there's any errors or there's any holes, no problem. With convergent modeling, you can clean it up. What it's really doing is it's eliminating the error-prone, costly process of reworking these pieces. So that is the convergent modeling. Next, topology optimization. Now, NX allows designers to create a completely new generation of product designs by taking performance requirements into account right from the start. Then the automated calculations, they iterate until it creates an optimized geometry. And it gives us this kind of organic, lightweight shape. But what's nice about this topology optimization, you can actually define where do I want my part to go and where do I not want it to go? What's the build envelope? And the topology optimization, it does the rest. And then you combine that with the convergent modeling, and you're able to easily create some really cool and efficient parts. Next up is latticing, or using lattices. We know that an important part of everything is taking out the weight, improving, let's say, fuel efficiency by making that car just a little bit lighter or that plane a little bit lighter. But we don't want a fuel efficient car or to ride in a fuel efficient plane that's not safe. That's where latticing comes in. You take out the weight, but you preserve the strength of the part. Now with NX and latticing, it's really incredible what you can do. NX, it has a bunch of, let's say, canned or a library of lattices, but maybe you need something a little bit more specific. Well, then you could create your own lattice structure. So these little squares that we're seeing here, you can optimize your own little shape. Another important thing that comes with additive manufacturing or designing for additive manufacturing is the rules and the checking. Because when it comes to creating these parts, a lot of times the designers, they can only think about creating parts with typical manufacturing processes, maybe injection molds, or if the part's going to be CNC designed. So they don't really know about the rules that come to additive manufacturing. A lot of times we'll just say, you can print anything. And so to speak, you can, but are you going to do it efficiently? Is your design going to work? Well, with NX, you don't have to worry about all that. You can set what's the wall thickness? What's the printable volume? Am I going to have voids? Or are there going to be any other areas that need support? And this is all built into NX with additive manufacturing. At Siemens, we believe that additive manufacturing is a technology that is reshaping everything. And we really believe in it so much that Siemens is investing heavily into additive manufacturing. Let's actually take a look at an example of what Siemens was able to do for one of our customers. And what you're looking at on our screen now is some vegetables. It's actually a fennel bulb. And you might be thinking, wait a minute, Dan, you put the wrong slide in here. Why are we talking about our lunch? Well, when I saw this demonstration, I kind of thought the same thing as well. How is it that you can use a vegetable, a fennel bulb, and transform it for additive manufacturing? Doesn't make sense, does it? Well, let's see how we can actually do this. So the goal of the project was to reimagine this high temperature burner system used in a fuel refinement process. So it was a thermochemical conversion process that burned the messy leftover reactants at an extremely high temperature to extract the fuel. Now the temperature in the chamber is so hot, it's above 1300 degrees Celsius, that it's higher than the melting point of the metal in the part. And you can see that there has to be a complex network of cooling to prevent this burner from melting. Otherwise, the gentleman here wouldn't be able to touch that without burning his hand. What was the conventional thinking on this part? Well, the conventional thinking was to create everything with conventional tools. But could we do something a bit more elegantly? Now, if you take a look on the left, you can see that the tip, it delivers multiple reactants into the combustion chamber. Within the burner, there is a network of ring-shaped channels that transfer the reactants and cooling water. And on the right, there's all these flanges, and they're connected to the supply system. So you get all these pieces made, and then you break out the welder, because you're going to have to do a lot of welding, welding these linear concentric pipes, welding the machine components. And you can see that the shape and the design of this burner, it all has to do with the manufacturing process. So how can you design this better for performance, and how can you reduce the cost? Well, here's where the idea came in. And that idea has to do with a term called biomimicry. So biomimicry, what that really means is we look to nature for our inspiration. You look at what the creator has made and try to copy that. There's some really cool examples of this when it comes to jet propulsion. Where did they come up with that? Well, they looked at octopus or octopi, or they looked at squids. Or for robotic arms, how can they improve that? Well, they look to an elephant trunk. How do you make a more efficient burner system? Well, you could look towards a fennel bulb. So that's biomimicry. Curtis, do you have any cool examples of biomimicry?
It's kind of funny, with that robotics team, we talk about this occasionally. And one of my favorite examples is to talk about the bullet train they use in Japan. That train had a traditional front end to it. And one of the things they found was when it exited tunnels, due to the air pressure differences, there was basically a little sonic boom that could be heard up to half a mile away. And they were looking at ways to change that. So what they looked at was the shape of a kingfisher, which is kind of like a crane type beak and head structure. And so they made this pointy front end. And not only when they did that, did they eliminate the sonic boom, it still made a little bit of noise, but it was nothing close to where it was. But I forget what the numbers was, but it was like a 15% improvement in fuel efficiency and another 10% faster, just because of that front end shape going 200 miles an hour. It made a big difference. But they mimicked the kingfisher's facial structure to make that nose.
Cool. That's the neat thing with additive manufacturing, is that you're able to look at things in nature, get inspiration from it, and then actually do something with it. Let's see an example of that fennel bulb that we were talking about. So here's the aha moment. The additive manufacturing thinking that inspired a new approach to solving their problem. See, additive manufacturing, it empowers us to create shapes we never imagined could be used or could be created with typical traditional manufacturing methods. Maybe you've heard the phrase, with additive manufacturing, complexity comes for free. So using that biomimicry, using that fennel bulb, that's how these researchers were able to take a look and say, well, what if? What if we could reimagine the burner and kind of shape it like that vegetable and then 3D print it? And what's cool about this is they were able to use NX to create a parametric model of this concept. Since it's parametric, that means if they needed a larger or a smaller burner, they would be able to do it and do it easily. And it's really incredible. The team, they really quickly achieved the optimal design by letting the computer do most of the work using generative design. And then they took a digital twin, took the digital twin approach by linking that parametric model in NX to star CCM for CFD analysis, and then to HEEDS to explore the design space of possible shapes. And this is the finished result. A much more elegant design that transfers the complexity of the system to the 3D printed burner tip. And it was a significant reduction in manufacturing effort and cost. Over 50% reduction in the number of welds, almost half the number of parts, half the size. And the team was also able to get some other increases. Reduced lead time. They made it to the market faster. And the design was adjustable. So when the customer had a different combustion need, they were able to meet that by using the additive manufacturing approach. So this redesigned burner tip, it achieved a uniform distribution of the cooling water and reactants from the pipe inlets to the ring-shaped surfaces over a short part height. So both requirements were crucial to fulfill the basic function of the burner tip and to ensure that it could be additively manufactured. And with the redesigned tip, it was possible to reduce the complexity of the conventional burner assembly as shown. The design concept for the new burner assembly is shown where the redesigned burner tip is connected through pipes to the supply system at the rear section. In comparison to the conventional burner, the redesigned burner tip enabled a simplified assembly by using pipe connections instead of nested ring-shaped channels. Now, although the redesigned tip possesses a high geometric complexity, as shown, it was easy because it was created using additive manufacturing. With conventional manufacturing, we would say to make these kind of shapes, well, what are you doing? You got to put some more blends on there, or you got to reduce the complexity, but not so with additive manufacturing. And when we look at this little chart, I just think it's pretty neat to see the differences. So you can see the size difference, the complexity difference. Imagine having all of your hoses coming out one side instead of coming out all over the place. The coolest thing about this study for me, though, was the number of parts and the number of welding seams. They put in here 45 to 50. That means that there was so much going on, especially in this front end where they were welding those concentric rings together. There's so much going on. How many parts were there? Well, between 45 and 50. It wasn't even precise. Or what about the number of welding seams? Greater than 43. Was it 44 or 45? Was it 48? We don't know. It was greater than 43. You see, there was all of these question marks. But when they rethought, reimagined the design, you can see the end result. And it's really impressive, isn't it? At Siemens, we're working to change the mindsets about industrializing AM, or additive manufacturing, across all of Siemens divisions and across all of their businesses. Because Siemens really sees additive manufacturing as being a key contributor to the future of all manufacturing. And we're designing and printing real production parts that go into products that Siemens is selling to their own customers. And the results are impressive. The parts are made in less time, perform better, weigh less, they're more durable, they're easier to maintain. Just think about the example that you're seeing on your screen right now for this combustion system. 13 pieces to 1. With 13 pieces, there's at least 13 opportunities for error. Or imagine just being able to get your product out that much faster, 26 to 3, and to make it lighter. It's because of rethinking the process with additive manufacturing. We've really learned a lot. We've learned that when you can shift your thinking from conventional to more of a DFAM, that's design for additive manufacturing, that when you can do this, you can transform your business with faster innovation cycles. You can reduce supply chain complexity and digital inventories. And we're seeing this play out in all sorts of different industries. Probably the best example that we're seeing this in that we can maybe relate to is in the orthopedic avenues. Right now, if someone were to get a knee replacement, well, they'll take a cutting guide and they'll get it as close as possible to your knee, and that's going to be what sets up the surgery. But with additive manufacturing and 3D printing, you can now take and match the patient's anatomy. So it's not something that's close to your anatomy, it is your anatomy. And that's going to assist the surgeon and it's going to assist you with that knee replacement. And that's just one example of reimagining, rethinking, and reinventing. Economics is really driving the adoption of additive manufacturing. And these two graphs, they're showing how additive manufacturing compares to conventional production. So based on the additive manufacturing capabilities available today, depending on your design's complexity and volume, additive manufacturing, it may be more economical compared to conventional production. And because this technology is advancing so quickly, if it's not economical today, guess what? It might be tomorrow, or it might be next week. There's all sorts of examples where additive manufacturing is just taking leaps and bounds in how fast they're going. And it's not just printing plastic. No, metal additive manufacturing printer companies, they too are rapidly increasing what they can do. They're adding additional lasers and additional automation to enhance their production efficiency and throughput. Software and process control also have a major impact on the economics of additive manufacturing. Now, there are limitations when we try to take advantage of additive manufacturing. We all know that when you have new technology, you have some new hurdles, some new roadblocks to overcome. In the case of additive manufacturing, there are all sorts of independent applications that don't work well together. So different file formats, different software, all these different things. And we're trying to take and translate them from one software to another software. And as that old saying goes, it just gets lost in translation. But that's where NX can come into play to really help with this. See, Siemens' vision with NX is to create one integrated end-to-end system for industrial additive manufacturing. So that connects a continuous digital thread all the way from the concept to the design, and then to the shop floor, and then all the way back again, back to the design. And then to drive this process with digital twins. We've fully committed to deliver this industrial strength additive solution and provide our customers the complete end-to-end process that eliminates data conversion between each step of the process. So you can reimagine your product designs, print products, and rethink your business. And you can do it with one fully integrated tool, and that is NX. So you can use NX for the design, the engineering, the manufacturing, the additive, and so on. NX offers tools to engineer and design the next generation of optimal designs for additive. Designers and engineers can take advantage of generative design topology optimization. That's the one that we saw where you let the computer assist, and it makes those organic, kind of bionic or funky shapes. We can also use convergent modeling, which is something that's unique to NX. We can use that to modify that topology optimization. Or if we have any scanned data, we can go in and work on that. And then we can take that finished design and validate it, make sure it's fully prepared and prepped for 3D printing, to make sure that the wall thickness is correct, that there's no voids, and that there's support where there needs to be. NX offers tools to directly use the designs in NX to prepare and simulate jobs for 3D printing. It also provides integrated tools to drive the post-processing and quality inspection of finished parts. So when you think about your design, from the start of it all the way to the final part, you can use NX. Even when it comes to the post-processing, maybe you're going to do some CNC work. Well, it doesn't have to leave NX. You can just imagine how this works, that you're going to have a design and a process that's seamless, a seamless digital thread from one end to the next. Siemens is teaming up with the world's leaders in additive manufacturing equipment and technology because they recognize the importance of maximizing the value of our customers' additive manufacturing equipment and our customers that they're requiring multiple additive manufacturing technologies in production and software that can define the applications for that additive manufacturing. As a result, not only does Siemens support the widest range of 3D printing technologies in one system, but Siemens and our partners are also pioneering new applications that are pushing the limits of what's possible. NX supports technologies for both metals and plastics. Now we're going to look at each one of these four in greater detail. But a lot of times when it comes to 3D printing, we think about that 3D printer that's just sitting on our desk and it has that little bit of filament and it's just kind of heating it up and running back and forth and printing. Well, there's new types of new types of technology that are coming out, such as a hybrid additive or multi-access using a robot, or laser material fusion. We're able to have all these parts and work with them. And then finally, this multi-jet fusion. This is a really cool one. And as I said, we're going to look at it in more detail. But it's just that you can print a lot of plastic parts and you can do it so fast that you can make the argument, in some cases, it's faster than if you were to make an injection mold. Now let's throw a question back to Curtis. So Curtis, which of these additive manufacturing methods or what other additive manufacturing methods have you used or seen?
Well, like you said, with the robotics team, we've done a lot of good things. But the coolest machine I've heard about or seen recently was a local company here. One of the people there called me up to tell me about this new product. It has a printing bed of 40 foot by 14 by 12 feet, so they can do up to something 40 foot long. It's amazing. And it's a plastic deployment, and they use powdered plastic going in pellets, and they melt it, and they actually put out, instead of some of these like desktop ones that put out a layer that's only a thousandth of an inch thick, basically a half-inch diameter rope as it's going through, because it's got to cover a 40-foot bed. It needs some speed, and what's cool about it is even with that large size, it's kind of rough. If you look at it, it's a bunch of ropes tied up next to each other. On the same head, it has a 4-axis machining head. So it can go back in and machine the surface smooth. And they're using it to make molds for the aerospace industry. So it's a very cool concept that they can make something that big. And they said if they had one application that needed to be longer, and they actually printed the two pieces, glued them together to make the one mold. So cool stuff just because of its size.
Wow. If I had a 40-foot 3D printer, just imagine the Tonka truck that I could build for myself, right?
Yep, or the Lamborghini that I'd like,
Yeah, there you go.
you couldn't
That's
afford.
cool. let's take a look at some other use cases. So additive manufacturing, it enables us to economically produce small lot sizes of parts. And when this is combined with the ability to scan the real world and then generate 3D models, you can have the power to offer personalized products. So here, what we're looking at is we're looking at somebody's knee that was scanned and the cutting guide that goes along with it. So it starts with a CT scan or with an MRI, and then we take that and use a little bit of convergent modeling to create the model. And you can kind of see just how it works. We get these all set up on the bed, and we're able to easily create these customized parts, customized pieces.
So Dan, I saw that blue material on here. Was that the support material to hold it up while it's printing?
Yes, yep. And that's the nice thing about NX. I'm glad you pointed that out, Curtis. With NX, once you create your part, you then go through those checks. And when you're going through those checks, it's going to show where do you need support. Because if you put support everywhere, it's going to be too expensive. But if you don't put support in the right spots, the part's going to sag. It's not going to work. So that's another cool thing with NX being that end-to-end solution.
So, support basically, if I'm making a bridge, the middle of the bridge would sag because there's nothing underneath it. So support holds it up during the curing process.
Yes, exactly. And if you think about that bridge example, it takes engineers a lot of time to figure out how to do that and make that bridge nice and sturdy. Well, we're taking enough time designing the part. We don't want to take and add a bunch of time figuring out the supports. So we let the software do that for us.
Very cool.
Yeah, I think so too. So another example is that designers and engineers, they can reimagine the next generation of bionic or organically shaped products that are optimized for performance and that can be effectively produced using additive manufacturing. Now, this use case is showing the powerful tool Topology Optimization. So we say, where can that part go? Where can't it go? And we let the computer do the rest. So the computer starts to iterate, which is what we're seeing, gives us a bunch of different designs, and then we're getting to look at the performance of each one. And that's going to allow us to pick what design do we actually want. So within the same system, manufacturers, they can prepare design models for 3D printing and post-print finishing. This maintains a continuous digital thread from the concept to the finished part. And the nice thing about this is when it comes to rework, well, it's eliminated when changes are made because we're having that a nice digital thread. And with NX, when it comes to CAM, no problem. It's one integrated solution. Additive manufacturing, it's also allowing companies to create really big parts. And that's kind of like, Curtis, like what you were just talking about. Now in this one, the video, it's showing how we can use an aerospace engine casing design to prepare for a multi-access direct energy deposition and then CNC tool paths to produce the part. Now this is kind of neat because this approach that you're seeing, it gives us a better alternative to some castings, forgings, and cladding. So we're able to provide tools to directly use designs in NX to prepare 3D print jobs for the most widely adopted powder bed metal 3D printers. And this is a seamless, smart model driven process, which means you innovate faster, save money instead of having multiple systems. Some of the advantages to this is that it's 10 times faster than fixed powder bed. and it can eliminate or reduce the need for those support structures that we had talked about. And the build envelope, it can be huge. As Curtis brought out, and the one that he had saw, it was up to 40 feet. And we can combine this with subtractive processes as well. There's also another one that we're looking at, and that is multi-axis hybrid additive. Now this is a pretty cool, if you're watching the video, we're getting to see that on one side, we're getting to see the NX, and on the other side, the real thing. What we're doing is we're using a multi-axis robot, and it's equipped with a Stratasys extruder and then a Cinemeric controller. And it's programmed, of course, using NX. So this technology is impressive because it's so flexible. On that robot, right now, it's doing carbon fiber is what we're looking at, but you could change what you're printing with. NX is also certified to drive the new HP Multijet Fusion 3D printers. Now this printer is impressive because it can produce high quality production parts faster than most FDM and powder bed printers and at half the cost. This technology, it's really revolutionizing how plastic parts are made by providing a viable solution or a viable alternative to expensive and long lead time items like injection mold tooling. And what you're noticing on the screen right now is we're able to take all those pieces and then optimize where do they go. We're able to nest them, but not just on a flat surface. We're able to nest them within that design envelope. And this is an automated process, but just imagine the amount of money that we'd be able to save with this. If you notice this chart, you can see that a study that was done, it really shows that Siemens is taking the lead in additive manufacturing. Really, each one of these different spaces, Siemens is at the forefront. And we bring that out because with NX, as we brought out, everything is together. It's one digital thread, an end-to-end solution. Nothing's lost in translation as we're using these tools. So to summarize, industrializing additive manufacturing can have a significant impact on products, manufacturing operations, and on business. So Siemens offers 3 key advantages to help you industrialize additive manufacturing. Number 1, and I've brought this out a bunch, it's an end-to-end solution for the next generation of design. Number 2, Siemens offers modular consulting services to accelerate time to value. And then lastly, Siemens has a global ecosystem for design for additive manufacturing know-how, digital inventories, and then distributed production. So with additive manufacturing, it's really breaking things up. It's really a disruptive technology. We could think about it being as disruptive as when we went from 2D CAD to 3D CAD, or when we went to the old manual hand crank Bridgeports to CNC machining. If you get into industrializing additive manufacturing, what are you going to do? Well, you're going to reimagine the products that you're making. Maybe you're going to make something that looks like a fennel bulb or a kingfisher. You're going to reimagine your business. Imagine having zero inventory because you're able to print on demand. Imagine being able to design anywhere, print anywhere, and be more competitive. And then you're going to reimagine your manufacturing. Imagine if you didn't have to have so many molds, so many castings, so much tooling. Imagine if your designs and the process could be simple. Imagine having an affordable, low volume production. Well, You don't have to imagine any of these things. You just have to start looking at industrializing with additive manufacturing. Well, that's going to be the conclusion of our little webinar that we had today. First of all, thank you, Curtis, for being on and for giving us your insight. Especially, it was nice to hear about how a high school is using additive manufacturing. And also, we want to thank all of you that were able to attend. We went through a lot and we did it rather quickly. So likely you do have some questions. And if so, feel free to send us an email at the email address listed there. And also, if you've got your phone out, go ahead and scan that QR code. That's going to take you to a link to more of our upcoming events and our upcoming on-demand or our on-demand webinars that we have. So at this time, we want to thank everyone and wish everyone a great day.